So now, having done isotopes and abundances, we are going to now look at an apparatus called the mass spectrometer, which in fact is the apparatus and the instrument that lets us determine the different isotopes of an element, the isotopic masses of each element, and their abundances. So the way this works, you don't need to know the internal specs of how it works. Just know that as the end result, it gives us as a graph. The graph is called a mass spectrum, and the graph has the total number of isotopes of each element that it takes a pure sample of, the isotopic masses of each element, and the abundance of each of these isotopes. And basically, maybe I can use chlorine to show the example of a mass spectrum of chlorine. Now, if you remember, chlorine has two isotopes. We've seen that already. We know that they were chlorine 35 and chlorine 37. And we figured that through data that we actually got from the mass spectrum that their abundance is for 75% and 25%. Now, how did we get that? Well, we actually used mass spectrometry, put pure sample of chlorine in there, and the end result that the apparatus gives us is a graph. And the graph is most crucial. It looks like this. It has isotopic masses on the x-axis. So if it's chlorine, the masses would be 35 and 37. There'll be lines on that. These are called peaks or signals. And the intensity or the frequency on the y-axis would also correspond to percentage abundance. So here, this is what the apparatus tells us. It just gives us a graph where the number of lines tells me the number of isotopes. Here clearly chlorine has two isotopes. The lines occur at the x-axis value of 35 and 37, which tells me that the one isotope has a mass of 35 and one has a mass of 37, and their abundances or the heights are 3:1 ratio or 75 or 25%, which then tells me their abundances are 75% to 25%. That's literally what the graph gives us. And why are we doing this? Because at times you won't get isotopic data from tables, you'll get them from graphs like this. So if I didn't give you this, but you only got the graph, then you look at the graph, say, okay, at 35 and 37, there are two isotopes. The heights are 75, 25. Okay, now using this, I can find the average mass of the chlorine atom, or the relative atomic mass of chlorine can be found through this method. So let's take a look at some examples of how to use graphs to find relative atomic mass. So here is an example of the mass spectrum of neon. Now if you notice here, the mass spectrum has three what we call peaks. So it tells me that I have three isotopes of neon. Neon with a mass of 20, because that's this fellow right here. That's a mass of 20. This fellow is a mass of 21, and this fellow is a mass of 22. And the mass of 20 has an abundance of 90.9. The isotope of 21 mass has an abundance of only 0.3, and the isotope of mass 22 has an abundance of 8.8. So this is the data we got from this graph, and literally just zooming out so I have more space, and I can just find the AR, that is literally the average mass. So X, the AR would be, I think this comes out to 20 point about 2, 1 to or approximate to 1 decimal place. So in this question, you can clearly see there are 5 isotopes of germanium, and the average mass would be basically 70 into 20.6. That's the first isotope. The second isotope's mass is 72, then 73, then 74, and then 76. So 70, and then you got 72 times 27.4. Then you got 73 times 7.7. Then you got 74 times 36.7, and the last one is 76 times 7.6, and all of this divided by the total percentage, which I went over would be 100, and therefore then let me just move this here. This will give you the average mass or the AR of germanium. So basically a mass spectrum just reads the graph and you do the math as you've been doing for isotopic calculations. All right. So in this question I see this, and this is a mass spectrum of an particular element that seems to have a small peak at 204, 206, 207, 208. So basically it seems to me that there are 4 peaks. So there are 4 different isotopes. Now the reason why they call ions is because every particle found in a mass spectrum is in fact of 1 plus ion. So the words ions here are referring to ions of isotopes. So if this element was X, this fellow is, every peak here is for X1 plus. This one is X204 1 plus. This one I'm pointing to is X for the mass of 206 and a 1 plus charge. 207 is X with a mass of 207 and a 1 plus charge. And the last one is basically the element X with 208 and a plus charge. Notice they're all of the same element, they all have 1 plus charge, because that is exactly the particle that has been measured and detected in the mass spectrum. You don't need to know how the ion is made. It's basically an ion of the atom of the isotope. That's all. So it's an ion of the isotope, which for you guys is, we only have to deal with masses, so we treat the atom and the ion the same mass, because when it loses an electron, electron's mass is negligible. So even though we've seen a few graphs for mass spectrum, they technically were for 1 plus ions of the isotopes and not the isotopes themselves. All right. So there are 4 isotopes, masses of 204, 206, 207, 208. And this is make rough estimates of the proportions of these ions. So my recommendation is you take a ruler and you measure the lengths of these out in millimeters, and then the length of one over the total length into 100% will be the abundance of each. So let's say the total is 10 centimeters and this is 2.2 centimeters. So the abundance will be 2.2 over 10. I don't have a ruler here, so I can't do this, but if you, in the exam, you can literally take a ruler, measure the lengths of each and add them up, and then individual lengths over the total length into 100 is the percentage abundance. That's how the graph gives out the length of each peak is in fact in the ratio of percentage abundance. Yeah.